Okay. Yeah, so I want to say a little bit about the tenfold way. One
Okay.
interesting general thing is that it's mainly been studied by condensed matter physicists, and some of them are pretty mathematical, but they're not really mathematicians. So some of this stuff is a little hard for me to understand, like what they're assuming and what they're doing. And there are lots of different viewpoints on the tenfold way. And part of why it's interesting is all these viewpoints. But I'm struggling to figure out how they all fit together. So I'll start what I think of as sort of maybe one logically good starting point. So it's all about Z mod 2 graded vector spaces. And so all sorts of things are going to be Z mod 2 graded. In particular, there's a concept, and I guess I'll call that, just because that gets tiresome, I'll call them super vector spaces.
Okay.
And there's a concept of a SuperDivision algebra. I guess all these vector spaces I'm ever going to be talking about are finite dimensional. So like when I say division algebra or superdivision algebra, I mean a finite dimensional one. So what the hell is a superdivision algebra? So it's an algebra in the category of super vector spaces. So it's got some kind of multiplication that makes it, let's say, an associative algebra object in the monoidal category of super vector spaces. But what makes it be division? So A is like, one way to think of it is like it has an even part and an odd part. And so what makes it be division is that multiplying by a homogeneous element, an element that's either in here or in here, can't annihilate anything unless that homogeneous element is zero. So we could say, I guess I could just say it like this: it has with no homogeneous zero divisors, I guess is a quick way to say it. If you wanted there to be no zero divisors at all, then that would wind up being very restrictive in and so a better thing to say is no homogeneous zero divisors. And so I could dig into them, but the main theorem about them is that, like, well, over the reals, I guess I didn't even say what we were talking about here, but algebras over the reals, there are just 10 superdivision algebras. And so that's sort of the quickest way to see where the 10 is coming from in the tenfold way. So now okay, I mean, so there are all sorts of things I could in theory do, like I should like explain what they are or something like that. But instead, I think I'll just get as quickly as possible to some mysterious thing. So so it turns out to be very interesting to look at the category of representations of a super, or maybe that's probably a funny way to put it, the category of, let's say, modules of a superdivision algebra. So those are like Z mod 2, sorry, I guess I'm saying super. So I guess when I say module of a superdivision algebra, I mean, it's the sort of obvious thing. So it's a super vector space on which that superdivision algebra acts, just in the usual sense of like a monoid object in a monoidal category acting on something. So it's very interesting to think about these. And these categories of modules, they act sort of like categories of vector spaces in a lot of ways, because division algebras are a lot like fields, and so they're like the category of modules of a superdivision algebra will be some semi-simple category enriched over the real vector spaces. And so for some of them you're very familiar with. So like some superdivision algebras include the purely even ones. So there are three purely even ones that only have stuff in the even grade, and those are just reals, complexes, and quaternions. So you've probably thought a bunch about modules of those, at least the first two, maybe the third. So anyway, so these are all interesting, and it's so let me call it like so we get a category of these. So let's like, I guess people would call it like A mod be the category of these modules. So when you're thinking about modules of algebras or of superalgebras, the notion of Morita equivalence naturally springs into action, because two algebras or superalgebras are Morita equivalent if their categories of modules are equivalent, if and only if. That's just, you can take that to be a definition, as you know. So then there's this. So then we get to this theorem that I consider somewhat mysterious, even though I know one way to prove it, which is that every superdivision algebra and I guess here, I mean, just to be careful here, over R, is Morita equivalent well, okay, this is a dumb way to state the theorem. Is a Morita equivalent to a real or complex Clifford algebra? Maybe that's a dumb way to state the theorem so far, because actually, unless I'm really screwing up, actually every superdivision algebra is a real or complex Clifford algebra. But I'm not done with this sentence yet, which is and vice versa. So every real or complex Clifford algebra is Morita equivalent to some superdivision algebra. Now here I realized that this statement is sloppy. The statement is sloppy because a superdivision algebra has to be Z mod 2 graded. And Clifford algebras aren't, in general, Z mod 2 graded in some God-given way. I guess they're Z mod 2 filtered in a very natural way, but they're not graded. So it's actually really important here that I should insert this caveat here. Real order complex Clifford algebra with some choice of Z mod 2 grading on it. And it's really important actually because we can take the quaternions, for example, and we can, so that's already a Clifford algebra, but we can put two different Z mod 2 gradings on it. We can put one, or at least two, I think two. We can put one on it where it's like all even, and I mentioned that, but there's another one where it's not all even, there's even and odd parts. And so those count as different super algebras then.
Does that happen already with the complex numbers?
Yeah, that's probably, yeah, I don't know why I'm, yeah. Yeah, so that's even easier to see. So yeah, there's another grading on the complex numbers where one is even and I is odd. Yeah, that's a good example. So some of these superdivision algebras that we're getting here are just your friends, the ordinary division algebras, but given different Z mod 2 gradings. Yeah. So this theorem here is sort of what I want to understand, I guess. So the way I know how to prove it, maybe I'm being stupid. Maybe everyone knows some better way to prove it than me. But the way I know how to prove it is to just do a case by case check that that's true. And that's not completely pointless because they're all really worth getting to know individually. And it's also famous that there are 8 Morita equivalence classes of real Clifford algebra and 2 of complex. So that's another way to begin sensing this tenfold, this tenness. But I want there to be some really good explanation for this. And I guess one last thing I'll say in this batch of ideas is that you can. No, I think I'll quit here. There's like tons more stuff to say, but this is like a good place to stop.
Okay.
And then like throw it open to you to ask questions or tell me things. This is like really important in physics these days in the applications of the tenfold way. Yeah, I'll say a couple more things. So physicists will sometimes sort of start out thinking, oh, the tenfold way, it's all about condensed matter systems with fermions, and they study these fermions using Clifford algebras, and then they work their way into the tenfold way that way. But this superdivision algebra approach doesn't sort of, at least doesn't seem to be starting out with talking anything about Clifford algebras or fermions. It's starting out with a very, very broad concept. And this very broad concept is also really important in physics because Schur's lemma says that when you have like an irreducible representation of a group, the endomorphisms of that representation form an algebra, and it's a division algebra. Because if you had a zero divisor, you could use that to split up your representation into smaller pieces. And so since quantum physicists love irreducible representations of groups or of Z mod 2 graded groups these days, you just are naturally led into thinking about superdivision algebras just from studying irreducible representations of those things, which are sort of like fundamental ways that the group can act. And that doesn't seem to have any, that when you first hear about that, that doesn't seem to be saying anything about fermions or Clifford algebras. So that from that point, that's what I'm really interested in, is like why is it that starting from this stuff that doesn't breathe a word of, well, breathes a little word of fermions because we're working in the Z-mod 2 graded world, but it's nothing about like spinors or Clifford algebras. How starting from there, we're suddenly like led to them by this theorem. That's sort of what I'd like to understand. It seems like a little mystery to me that could be potentially a cool answer, like the birth of Clifford algebras out of nothingness or something like that. Okay, that's all I have to say. Yeah, that's sort of the philosophical cloud that I'm inhabiting there.
Well, I have mostly just silly questions. Again, partially based on a lack of feeling about when we talked about this before. But first of all, what's the definition of a condensed matter physicist? You don't have to go into detail, but I probably should have some vague idea. But
they like to study.
I mean, that is right. That's a little bit striking that you come out and say that, oh, this branch of mathematics is mainly the province of condensed matter theorists. I mean, you didn't say it's physicists. You said condensed matter physicists or something like that.
Yeah. So, well,
you work with fermions.
Condensed matter physicists are trying to classify states of matter.
Matter is mostly fermions, but no.
Yeah, matter has a lot of electrons. For them, it's like, yeah, you got like a crystal or an amorphous thing, and the electrons are sort of the ones that like get to do stuff, whereas the nuclei are basically staying put. This is solid matter.
Is condensed matter physicist, is that like the opposite of a field theorist or something like that?
It's a Wick rotated field theorist. They use a lot of the same math as quantum field theorists. So there's a big overlap in their mathematical technology, but I'd say it's this quest to classify states of matter that led some condensed matter physicists to claim that there's a certain way in which you can classify some kinds of states of matter into 10 different kinds, and that's what made them get interested in the tenfold way. They had a lot of specific ideas about what
they think they had this list of 10 things before they had an analysis of it in terms of superdivision algebras. They started out by thinking of it in terms of
whether things have time reversal symmetry, whether they have
this
particle, antiparticle, particle hole symmetry, or various combinations of the two.
All right, I'll have to
there's a way to get 10 things out of thinking about that. And then they realized that you could like get examples of these 10 different kinds of possibilities by looking at systems of fermions, systems of fermions interacting with a quadratic Hamiltonian, which are quadratic in the annihilation and creation operators. Quadratic Hamiltonians are like the nice solvable ones.
Yes.
And so then they noticed that what they were doing there was really looking at different kinds of Clifford algebras. And so they like set up a correspondence between this time reversal, charge conjugation, symmetry, classification, and different kinds of Clifford algebras. And then they wound up connecting it to other things too. The main thing that I completely resisted talking about in this little mini presentation was symmetric spaces. So Cartan had classified, let's say, like compact symmetric spaces, for example, although he did other stuff. And then it turns out that there are like 10 infinite series of compact symmetric spaces. And it turns out that those are correlated to these other things. I want to talk about that sometime too. But
Okay, that's interesting. That's interesting.
and so the physicists had some theory, which I'm really confused about how that fits into the physics as well.
Okay, I just throw out more silly questions. So here's a really silly one. Is there any particular relationship between condensed matter physics and quantum computing?
Yeah, there are people who are trying to do topological quantum computing are trying to make up states of matter with interesting properties that could support quantum computing.
Okay, that was just a very, very silly question. So this
there's a guy named Kitaev. There's a good name to know, which is a guy named Kitaev, who's involved in
spell that
KITAEV.
Okay.
So he's involved in this tenfold way stuff, and he's also very interested in like making up new states of matter, some of which could be good for quantum computing.
Okay, this way of making the complex numbers into a into a super thing. The complex number has a super structure on it. So, and it's not supercommutative.
Right.
And when you tensor it with itself as a thing, it gets even sort of less supercommutative, and that's the thing that you were talking about the quaternions.
That could well be. So if you tensor two of those complex numbers, one of them has an I and the other has a J, and they're both odd. So in the natural tensor products for super things, they would anti-commute, and their product would be called K. so and it would be even again. So yeah, you're right.
Yeah, I think I've heard somebody comment on this.
Yeah, so that gives you like a Z-mod 2 graded incarnation of the quaternions. There's also the purely even quaternions running around in this game.
Right. Okay. The
super tensor product of Clifford algebras is always in like another Clifford algebra in a very nice way. But that super tensor product is different than the tensor product just as algebras, because the rules for commutation are different.
Well, I mean, that sounds like there's just a that sounds like that the Clifford algebra functor is a monodal functor from the sort of quadratic sum of quadratic form spaces or something like that. There's sort of an obvious.
Yeah, that's right. And that's a really good way to think about things like bot periodicity, because if you like to look at, it's more exciting for the real Clifford algebras, of which there are like 8 different kinds. And so you can start out with the one that has a single square root of -1 that's an odd element. So that's like the complex numbers. That's just what we were talking about, the complex numbers that viewed as a super algebra. And then it can keep tensoring itself with itself over again, and you march your way around the bot clock and get all the other real all the different kinds, all the real Clifford algebras with various numbers of square roots of -1.
Okay, a lot of these things I'll have to really think about later, but they sound very reasonable. Another sort of silly question here is like, so a word we didn't say here, and maybe I'm not sure I like this word, or I'm not sure I like all the different ways that this word is used. But some people, when they're talking about Tanakian philosophies of some people, Tanaki gets used to mean a bunch of different things, but some people use it to mean something like just the general phenomenon of and you have an algebraic object, and you have a category or something like that. And you have some sort of correspondence between the types of algebras and some sort of correspondence between the algebras and the categories that you get from some kind of modules over them or something like that. And something like that is sort of going on here, but at a very primitive level. I mean, is that true?
Yeah. No, that would, yeah.
I mean, it's like you know, when some people are trying to set up certain Tanakian correspondences, they have it at a very centipede level. They have a thing where you don't have both a multiplication and a co-multiplication. All you have is just a multiplication or something, and see how far you can get with that. You can't get very far with it because you've pulled almost all the legs off the centipede, but it's that kind of thing.
Yeah, so these are just, these superdivision algebras are usually just algebras, by which I mean that these categories A mod, usually some of them are nice symmetric monoidal categories in a good way, like the category of real vector spaces or the category of complex vector spaces. But a whole bunch of them are just, they don't really want to be monoidal categories that way. But what they do have is that you can tensor an object in one of them and an object in another one of these ones and get an object in another one. So they should all be sort of thought of together, and that's where this super Brouwer monoid I was talking about. I was avoiding talking about that aspect of things here, but that's another aspect I really find cool because it's unifying all these 10 different superdivision algebras into some larger structure.
So I think the last time you did start talking about this stuff, I did comment on something about the idea that that my sense, right, that if you invent a concept of real 2 Hilbert space, then there's like maybe 3 different kinds of atoms, you know, in such a thing.
Yeah, thanks for reminding me of that. That's sort of what I'm thinking about here for the ZMod 2 graded case where there are like 10 kinds, but I haven't thought I've been thinking about it, but not thinking about 2 Hilbert space right now. But maybe that is probably the good way to think about it.
Okay, so do I have anything else close to intelligent to say? Maybe not. Let's see. Again, I have the feeling that I really need to.
I mean, one thing
go ahead.
Sure. Yeah, I don't expect you to instantly spit out profound ideas if you haven't thought about something yet. But
well, I really feel like I do want to go back and review the previous, even sketchier discussion.
Okay.
Started on this.
There's another thing that's really fun to do, but takes a lot of time. And it might be more fun for me than for you. I don't know. Is to actually like but you like this type of stuff. It would be to like go through the 10 superdivision algebras and sort of examine and what they're like and what these different module categories are like, because they're very nice. You know about a whole bunch of them. there are a bunch of.
It's possible I might know about all of them, sort of, but.
So like one kind of thing that like so you know that like. Well, this is like a non-super version, but like that like if you tensor the complex numbers with themselves as a real algebra, you get C plus C, which is like the categorification of 2 times 2 is 2 plus 2. And so that like the category of modules of C tensor C is the category of split complex vector spaces. Where by split, I just mean that they're like
Yes.
Yeah, not that they're split means other things in this world, but yeah, just it's written as a direct sum of two parts. So some of these A mod categories are categories of like split real complex and maybe even quaternionic modules. Yeah, that's right. And so then there are other ones. And so they're all interacting with each other in lots of fun ways. That is, they have a lot of individual distinctive personality, and they tend to be things that you sort of bump into here and there.
Yes. Yes. All right. Let's see. Is there anything else I want to? Might be things I'm forgetting to say here, but let's see.
That's fine.
Okay.
You can email me if you think of something.
Okay. Okay. Okay.
I'm happy and eager to move on.
Okay. Okay. So we're going to let's see. I guess I'm gonna turn on my screen sharing or something here. So turn the screen sharing on. Why is it doing that? Sorry, I'm just having annoying problems here. All right, let's see. So actually, you know what? This might be a good place to just break the recording. Just so I can set up some things.
Okay, sure. I'll pause it right now. Okay.
Okay, so in the time we have here, I'm going to try to talk more about designs and I guess sometimes called dessins d'enfant or something, Grothendieck's and Grothendieck-Teichmüller stuff and something like that. So one of the things that's going on here is that you might have noticed that as I've been talking about this Grothendieck-Teichmüller stuff over the past several weeks or however long it's been, I've as usual been, you know, using my usual methods of just trying to reinvent everything for myself, and only much later trying to find out if I'm doing anything similar to what the textbooks say I should be doing. And but I finally did get around to looking at some, not exactly textbooks, but some papers and stuff on what the Grothendieck-Teichmüller group really is and stuff like that. And it turns out that there's a really interesting relationship between the things I've been trying to reinvent and the things that these papers I've been looking at say about what the Grothendieck-Teichmüller theory really is. So I'll have to try to demonstrate that as we go along. But first, so I'm got many things to try to explain here. Going to go in a very disorganized order here. The first thing I want to talk about is there's a style of, we've talked about different drawing styles for the designs, and how, you know, some of them are just more convenient for various purposes than other things. So there's a particular style of drawing the designs that I ran into recently that I like for certain purposes, and I just want to demonstrate it at the moment. Okay. So I guess it's based on this idea of what a lozenge is. So a lozenge is the basic building block from which these designs are built, and they're kind of like quadrilateral shaped. And and in I have the tendency to use colors to show how things work. And so I've got these corners of this quadrilateral. No, that's the wrong color. It's supposed to be blue. This is supposed to be the color scheme for the corners of these so-called lozenges that are quadrilateral shaped. And so what I want to, the way I want to draw these lozenges in this drawing style is I want to put little rotational arrows at the corners. So that's a little green rotational arrow at the green vertex, indicating that that's a thing you can do with these designs, is you can rotate to the next lozenge over at the this is one of the generators in the I guess that it's supposed to be, these things are supposed to be actions of the free group on two generators, and the two generators are supposed to be rotate around the green vertex and rotate around the red vertex. And so that's that little green arrow. So that little green arrow that I drew, it has both a head and a tail. You can see that it's got a head and tail. And same thing with the red arrow. And the fact that it's got both a head and a tail is supposed to indicate that it's a complete rotation. There's, these are little sort of like 90-degree rotations. I mean, right? They're just. Maybe I shouldn't even use angle measure, but you just have to go. You just have to go one step like that, and that's a complete rotation. But the blue ones work differently. Yeah, were you going to say something?
What do you mean that's a complete rotation?
That's how you perform the. I'm not saying very well. That's how you perform the complete. I mean, so this free group on two generators acts on the collection of lozenges of the diagram. So, for example, there's another lozenge over here. Sorry, there's another lozenge over here.
Yeah.
And it's got what is it? I guess it's got like blue there and red there, something like that.
Yeah.
So if you're starting out in this with this one,
yep.
And if you perform the green rotation, it gets you to this next one over there.
Okay.
If you perform the red rotation starting from the asterisk one, then it gets you to over here.
Yep.
But what happens if you perform the blue rotation? So I'm going to try to draw the arrows for the blue arrows to indicate how the blue things work, because it's a little bit tricky. So these are all going to be all the rotations that we're interested in here. We think of I tend to think of clockwise rotations as primary. So you can see I'm drawing all the little arrows that I'm drawing are all clockwise. So right here I've got. No, sorry, I did that wrong. Let me fix that again. That's supposed to be an arrow that doesn't have a head, it just has a tail. That means that it's incomplete, it's just half of an arrow. And the other half, or another half, is sort of down here, which just has a head and no tail.
Yeah.
So the idea is that if you want to perform, there's another one over here, another lozenge over here. And what does it have? It has blue in there and red in there.
I see.
And, it all fits together. So like this one would have like that there. So the point is that when you do the blue rotation, right, the blue rotation, you can work this out that the blue rotation, you have to sort of go twice to do the blue rotation. But also it's not really an independent rotation, right? I mean, the whole free group on two generators is generated by red and green alone. So this is like, I guess it works out that if, you know, in some order, it's like the green rotation and then the blue rotation and then the red rotation, and that equals the identity. You can check that if you do this, you'll get back. So, yeah, so, you know, there are certain conventions you have to set up to get this to work. So, but you have to get those, you have to set up those conventions anyway in order to get the thing to work anyway. So it's so the conventions that you need to use to get the drawing style to work are good to be constrained by anyway, because they're so right. I mean, you see one of the blue dots, one of the blue vertexes has just head and the other one has just tail. The convention for that is, let's say that the blue dot at the top is the one that just has tail, and the blue bottom, the blue arrow at the bottom is the one that just has head. I mean, you can use whatever convention you prefer, but but how do you know which blue vertex is at the top? Well, so my convention is that green is on the left and red is on the right. So this is, you know, this one here is the one at top, this one is the one at bottom. And yeah, so this is yeah. So I find this style useful for certain purposes. If I don't use this style, I get really confused about how the rotations work. You know, if I just draw the designs and then try to do the rotations, I get confused. But if this has such complete information about the rotations that once you get used to it, it's very easy to see how the rotations work. Okay, so that's one thing I wanted to tell you about. Now, there's I guess there's yet another drawing style that I find convenient for certain purposes. So, and I'll just try to quickly explain that drawing style. So, I'll particularly use this drawing style in the case of the Gaussian designs and the Eisensteinian designs, because those are, you know, those are based on these. Those are special cases of this cartographic thing, where instead of having the Coxeter diagram that's shaped like a triangle, you have a Coxeter diagram that's shaped like a straight line, because the generator at one end and the generator at the other end commute with each other. So, you know, so an example of these is the Gaussian designs, which are based on the Gaussian integers. So like, this is supposed to be a picture of like a little piece of the Gaussian integers. And then each is in its own Voronoi cell. But then you've also got these deep holes between the Gaussian integers. Again, it's probably overblown terminology in this simple context, but you can call these the deep holes. And there's the dual Voronoi cells, which have these, you know, I'm drawing the walls of the dual Voronoi cells in green. And it's like this and like this and like this. And sorry. And so you have Voronoi cells and dual Voronoi cells. And the lozenges in this case are the intersection between a Voronoi cell and a neighboring dual Voronoi cell. So we have, you know, like, let's say our favorite Voronoi cell is maybe this one here. And our favorite dual Voronoi cell is neighboring it. And so the intersection between those is one of those lozenges. And you can see it's got, well, we can also draw in the blue ones, right? Which are the intersection points. So they were like,
Yep.
and so you see, we're getting the same pattern of, you know, a quadrilateral with two opposite blues and a green and a red. And I guess in this particular case, following the convention that I was using over here, I guess this blue over here would actually be the top blue, whereas this one over here would be the bottom blue over here. But so this just, you know, this just helps me to understand how the lozenge is the intersection of the Voronoi cell and the dual Voronoi cell. And
Is
those
that
dual,
true in the
Yeah.
is that true in the Eisensteinian too?
yes. Yeah,
Uh-huh.
should I try to draw that one? Or
You don't need to. I mean,
Okay.
I'm just curious. Like someday
Yes.
you will, I'm sure. But
Yes, it works in any of these cartographic cases, which again is where this the Coxeter diagram is this straight line Coxeter diagram. So
mhm.
yeah. All right, so that's just a couple of things that I wanted to say. So now let's try to I want to show you some mathematical stuff. So first of all, we have to hope that the Mathematica is going to work, and if it doesn't, then we'll stop the recording. And so let me see if I can get the screen sharing to work here. So I'm changing the screen sharing from this thing over here to this other window. Where is it? What's it look like? Where is it? Where is it? Where is it? Okay, there it is. Okay, you can see that?
Yep.
Okay, so you can see that this is a design that Mathematica has drawn for us.
Okay.
You can see it reasonably well? What?
Yeah, I can see it. Yeah, I'm just not used to the designs that look like this. I don't know why.
Can you say why? What's?
Oh, just your style of drawing always looks so completely different than this.
Oh,
This is
oh
too
yes,
beautiful
yeah,
or
that
too
could be.
something.
That could be. But so
I guess,
this,
yeah. Uh-huh. So what is it? It looks very conformal, projection-y.
yeah, I'm still a little bit mystified by why it has this very strong circular feeling to it. I'm not sure. Let me show you another one here. So this is supposed to be there's a pair of designs here that I think are in the same Grothendieck-Teichmüller orbit, and that's a big part of why I'm showing you these pictures. So let me see if I can find the other one here. So this one is, you know, if I could have, if I hadn't been so lazy, I could have drawn improved versions of these pictures that would make it a little bit clearer what's going on. This particular one that I'm showing you here is a little bit hard to see because you know it ends up having some vertexes that are very close to each other, and it's hard to, you know, there's a spot there. Where is it? Right there, where it gets very crowded. So I had to magnify that spot, and then this down here is a magnified picture of that spot. So so these two drawings are, I strongly suspect, in the same Grothendieck-Teichmüller orbit, and that's a big part of what we're trying to understand here is how and why, and you know, these two designs are in the same Grothendieck-Teichmüller orbit. So let me go back to this one for a second. So, right, in this one you can see pretty clearly. I'm hoping you can see pretty clearly what the vertex census is of this one. Okay, so let's keep track of the vertexes of the various colors. And and, take a census of the vertexes here. So for the green vertexes, you can see there's 2 of them, right?
Yep.
And I guess I'll call them A and B. And I think A is my name for the one that has, well, you can see that the 2 greens, right? One of them is sort of busier than the other, right?
Yep.
So yeah, so it's I want to say like the root multiplicity at the less busy one is 2, and the root multiplicity at the other one is 4.
Mm-hmm.
So I think A is the one where it's 2, and B is the one where it's 4. So that means the Young diagram, that we're dealing with here is, I guess, like this, 4 and 2, and I guess it worked out that the top row is labeled B and the next row is labeled A or something like that. Now, for the
So green is root, green is zeros.
yeah, I mean, okay, so some time ago, like, I don't know, a couple of weeks, I talked about this idea that you can think of a rational function. So, right, this picture is the inverse image of the real line under a rational function. That's what this picture is.
Mm-hmm.
And the green dots are more precisely, something like the zeros, and the reds are the infinities, and the blues are the ones or something like that. But of course, by the triple transitivity, it's very much a matter of convention.
Right.
And,
No, I was just asking about your convention. Yep.
Yeah, but I'm not even sure I have a convention. I'm going to be,
Okay.
It's because what I do with this is what am I trying to say? That there's this idea that a rational function is really an affine linear path in the space of polynomial functions. And the silly terminology that I introduced in explaining that idea was, I talked about, the numerator of a rational function, the denominator of a rational function, and then the k-orator of a rational function. The k-orator is just the polynomial that describes the fiber over k, just like the numerator describes the fiber over 0, and the denominator describes the fiber over infinity. So yeah, I guess we're saying that the numerator here has 1 root of multiplicity 2 and 1 root of multiplicity 4. And so A is the root of multiplicity 2, B is the root of multiplicity 4. The denominator, yeah, I think in some convention, I at least started out with the denominator corresponds to the red. And and I think I called that G and H or something like that. And I think it was G was root multiplicity 4, H was root multiplicity 2. So again, it's the same Young diagram. But I guess this is G and this is H or something like that. Now, for the blue, that's the one-orator. Although, I may be playing in my program, I think I have some funny renormalization thing, and maybe it ends up being called the k-orator rather than the one-orator. But for the moment, let's pretend that it's the one-orator. And that one has, you can see there's 4 blue dots, right? So there's like C.
So 2 of multiplicity 1, 2 of multiplicity 2.
Yeah, so in the labeling scheme that I was using, B and F are the 1s and D and E's are the 2s. And it's a little bit hard for me to tell you which of the 1s is C and which one of the ones is F, because the program doesn't even really care or something like that. So, just like some ambiguity, or what's the word I'm looking for? I don't know. But so yeah, so this Young diagram would be like, it's actually the other Young diagram on its side. It's, it's got like, what is it? I guess it's like D and E are up here, and maybe C and F are down here, or something like that. And right, so
Can I ask a really digressive question?
yes, go ahead, go ahead.
Had you already, let's see, do there have to be the same number of boxes in each of those Young diagrams?
Yes, because
That's the
it
number
should
of
be. For what we're doing here, it should be. I mean, it. What am I trying to say? I mean, you can have a rational function where the numerator is a different degree from the denominator, but somehow that's a very that's too annoying to even think about. I mean, right? Generically, the numerator and the denominator are going to be the same degree, and well, I mean, I mean, partially, I'm saying is that if I had done this the right way, then perhaps I should, allow for. I think there are all sorts of things that I'm incredibly sloppy about here, and this issue of does a rational function have to have its degree, the degree of its numerator and denominator? Do they have to be the same degree? Well, no, but we might as well. I think
Okay,
it turns out there's no harm in doing it.
Yeah, okay, I see what you mean. I think that if you generically,
Yeah,
I don't, it's too complicated to explain, but
right. If I was doing this in a very clean way, then I would not have all this sloppiness, but I do have a lot of this sloppiness.
Okay.
So, this is like what, this information, this triple of Young diagrams is like what I call the vertex census. It keeps track of, the multiplicity of the vertexes. And you can see in the picture the way it's supposed to be. But so, right, we sort of have to consider the way my Mathematica program works is that it tries to, right, I mean, the Mathematica program is sort of split up into different parts. You'll only see part of it here or something. But what it kind of does is it, you input the vertex census, and then it tries to write down this system of equations that says that you've got this rational function, this, given in terms of this numerator and denominator and kerator, and it tries to find all the solutions that, so yeah, I mean, right, I mean, what am I trying to say? Right, we're supposed to have an affine linear path in the space of polynomials. That's what a rational function is. That's that again, it's a slightly sloppy way of stating it, but it's roughly correct. That a rational function is an affine linear path in the space of polynomials. And those correspond to the each polynomial in the, well, when I say path, I really mean in it's really just a one complex one-dimensional affine linear complex one-dimensional subspace and each polynomial in the family that corresponds to the zeros of that polynomial correspond to the fiber of all the possible different fibers of the rational function. So that, yeah, that's the way it works. And so what the program is supposed to do is, first it forms this, it forms these three different 6-degree polynomials, where the coefficients, are themselves polynomials in these variables a and b and c and d and e and f and g and h. So like, the polynomial for the green polynomial would be x minus a squared times x minus b to the 4th. And then you can expand that out and, etc. And there's the blue polynomial and the red polynomial. And what the program does is it solves the equation or the system of equations that says that these three polynomials are collinear in the space of in the space of polynomials. And
Uh-huh.
and you know, and we've talked about how we have reasons to expect that this will actually give you a zero-dimensional space of solutions. And this all worked. So, I mean, you know, one of the things I'm saying here is I'm just saying, you know, this is good news that this, you know, perhaps sloppy way of doing this programming, it actually worked. It actually produced these kind of pictures. So, you know, I was.
So does,
yeah.
So you can solve the collinearity equations, and Mathematica will like list the solutions, and they'll be finitely, I mean, when you're lucky, well, you are lucky, and there are finitely many of them, and it lists them.
That's right. That's right. Now, at this point, I'm having Mathematica solve the system of equations in a numerical way, you know, as compared to some sort of symbolic way or Grosvenor basis way or something like that. So we're solving it in a numerical way. And so I you know, that means I can't completely trust, you know, whether there might be numerical overflows and things in some of the solutions. Like, so some of the solutions end up having vertexes really close together. And for those, I get very suspicious. And I think that, you know, maybe that's just an artifact of the numerical solution process. But, well, okay, so.
You mean,
yeah.
What would happen if the vertices actually were at the same point?
That's important too. That's important too. Those should get ruled out. Those should get ruled out. And you know, there should be an easy way to rule them out in the program. I wasn't industrious enough to actually get the program to take care of that, but I did check that numerically that it looked like okay. So right. So first of all, this is supposed to this should theoretically, you know, if things work out, this program should produce all of the designs that have this vertex census. And in fact, it succeeded in producing at least 2 of them. And those 2 are the ones that I was really interested in the first place, these Gaussian designs that are related to the Gaussian elliptic curve. And so that's really big, you know, I consider that a big success. But I'm not really sure how many other designs it should have produced. I mean, you know, how many other designs could there be that have this same vertex census? I never quite figured that out. It would be easy enough to write a combinatorial program that would answer that question, but I never quite got around to doing that. So I'm not sure how many other genuine solutions this system of equations should have. Can you
just start? Is it good enough to start drawing topologically correct designs?
Yes. That's all you have to do. You just have to kind of, you know, completely enumerate all of them. And it's a, you know, it's a little combinatorial project that I wasn't quite, you know, I was a little bit too lazy to actually finish doing that yet. So I'm not sure how many. I wouldn't be surprised if it turned out that, you know, maybe these 2 Gaussian designs, maybe these are the only ones with this vertex census, but maybe not. Maybe there is a bunch of others.
Well, I mean, but Mathematica is claiming that they're the only ones, right? Sort of.
Mathematica is claiming that these are the only ones.
Are they? Is it? Yeah. Are they?
No.
I mean,
no. In fact, Mathematica claims that it found 751 solutions.
Oh.
And out of those 751 solutions, I think 100 of them looked like they were solutions that actually had the vertexes actually coinciding. So those are ones that, you know, absolutely should be eliminated. But that still left like, you know, 600 or something, or 500 that I didn't have a good reason to eliminate. And out of those 500, some of them should probably be sort of repetitions of each other, because just of the fact that, you know, you can, you know, C and F can be permuted and D and E can be permuted or something like that. So if I actually tried to figure, it might be that Mathematica is telling me that maybe there's like 100 or 200 solutions or something like that. And I really only wanted 2, and I'm getting these other 100 or another couple of hundred. And I don't really know what in the world they're good for. You know, they could be, it would be nice if they all turned out to be just numerical errors or something like that, but I'm not sure what they are.
I mean, did you ever spend any time just like trying to draw designs with these vertex censuses? other
think
than the
I
ones
did
that
that a
you-
little bit. I think I did that a little
you
bit.
feel a pressure pressing you to draw ones that you'd already got. Instead of like, I mean, the combinatorics of this looks complicated enough that I could imagine there being
Dozens.
more than 2 dozens of them. I don't know. I mean, but I don't have. I'd have to try to draw some to see.
Yeah,
if
I'm
I
really
felt
not sure. I
this.
have one intuition that says that there really might just be these two. And I have another completely contradictory intuition, which says that there's probably dozens of others. But but I don't think that's gonna, we don't have to, I don't think we don't have to,
Yeah.
I think it's okay to proceed with that uncertainty for the moment.
Mhm.
But you know, there are all sorts of fun things that I should get around to doing, getting Mathematica to figure things out. But so what am I trying to say here? Okay, so first of all, let's try to remind ourselves of where these two examples are supposed to come from. So they're supposed to both come from Gaussian design. Now, let's see, there's one Gaussian design that looks.
I can't see what you're drawing, by the way.
Okay, yeah, right. I have to go back to the other one now. Let's see. Yeah, I have to, right. And you know, there's probably something very inefficient that I'm doing here because I don't really know how to use all this Zoom stuff. But I'm switching back and forth between different screens that I'm trying to share here. So now I'm trying to share the other one that I had, which is this one. Right, now you can see my little,
Yep.
okay. So, I mean, that's a little Gaussian design. I'm drawing the sort of Gaussian integers in their Voronoi cells, and then it just wraps up like that, right? But then there's this other one, which we think is which I'm getting increasingly confident is in the same Grothendieck-Teichmüller orbit. And it looks like what? It looks like drawing that right? And I think it looks like, so again, it's got 3 red vertexes. And so I really just drew one of them so far. Well, okay, and then I just added the second one, and then there's the third one. And, you know, they're inside their Voronoi cells. So it's like this. So really there's just, you know, 3 Voronoi cells there, but right, this one is arranged differently, right? So, and on this one for the border outline, I drew it as a dotted black line because it's not really, right, it doesn't fit with the red grid of the Voronoi cells.
Uh-huh.
So yeah, so these are 2 different Gaussian designs. And again, there's all these different drawing styles. So one of the drawing styles that you can use is you can put in the greens and then the blues, and the blues go there. And right, so right, if you put it, and then I think if you put in all the things like this, it looks like this. Again, there are these very busy drawing styles, and there are these less cluttered ones. But this one looks like this. So this, yeah. So this is this pair of genus 1 Gaussian designs. But the high genus ones are at this point a little bit harder for me to understand. So I really like the genus 0 ones. So I can convert these to genus 0 just by, you know, modding out by 180 degree rotation around their center.
Mm-hmm.
And that produces these things like, you know, these examples that Mathematica is drawing for us. for us here. So for example, this one here with, with that little magnified detailed region there. This is the one that comes from this one on the left. What Mathematica is, oh, sorry. Again, I have to switch back and forth here now.
Yeah,
So,
yeah. No, I think I know what you mean. The one that has tons of stuff packed into it, almost a dot. Yeah.
yes. And whereas this one over here is the other one that Mathematica was showing. So yeah, in my notebook here, which I'm drawing freehand, I'm drawing the genus 1 ones, but I have Mathematica drawing the genus 0 ones, and that's partially because this k-iterator idea is, so far it's only really designed to work in the genus 0 case, and so okay. So first of all, okay, now I really do want to go back to the right. I say I have to switch back and forth between the screen sharing here. So where's the one I'm looking for here? Okay, so now you can see the Mathematica pictures, right?
Yep.
So let's just take a little time to try and learn stuff just by staring at the pictures. Because there are certain things that I didn't even think about too much until I started staring at the pictures. Yeah. So let's stare at the pictures a bit. So yeah, let me go back to this one here, the one with the little magnified section here. So one thing you can clearly see in this example, I think, is that it's got bilateral symmetry.
Yep.
And not only does it have bilateral symmetry, but it has all of the vertexes lying on the symmetry axis.
Mm-hmm.
Let's compare it to the other one now. So this other one, it turns out also has bilateral symmetry, but it's not manifest because somehow I used the wrong Möbius transformation or something like that. But can you sort of, but combinatorially, this one does have bilateral symmetry.
Where is the symmetry line? Which cursor?
Well, it turns out that there might be more than one way to see it. The way I originally saw it was that if you do a Möbius transform to make those 4 blue things on a straight line, then that straight line is the axis of symmetry.
Oh. So it's not any of the lines that's drawn.
That's right. That's right. That's right. It's not. Yeah.
Yeah.
That's right. That's right. The symmetry axis was actually a part of the other design. The symmetry axis in this one. Well, my friend was claiming that there might be, my friend was claiming that there might be a way to draw this one where this circle, this sort of thing that looks like a circle that the red and green dots are lying on.
Yeah.
I think my friend was claiming that might be, you might be able to use that as a symmetry axis. See, like, depending on which Möbius transformation you apply, you might get different ways of seeing this as bilaterally symmetric.
Right.
So there is at least one way, and possibly multiple ways, of making this, by performing a Möbius transformation, you can get this one to look bilaterally symmetric too. But
so does that have to do with real varieties or something?
Good question. Yeah, that's part of what's confusing. But in this case, even if you do manage to make it bilaterally symmetric, I think you will never get all 8 of the vertexes to lie on the symmetry axis. You can get all 4 of the blue ones to lie on the symmetry axis, and maybe you could do it the other way around and get all 4 of the red and green ones to lie on the symmetry axis. But as you're suggesting, that sounds to me like it has something to do with real versus complex or something like that. And I don't know what to make of this, and I'm a little bit worried. I'm not too worried. I think it's going to work out somehow, but I'm a little bit worried that, when we see this as being in the same Grothendieck-Teichmüller orbit, in the same orbit under the action of the absolute Galois group, it almost seemed like a paradox to me. But presumably it's not a paradox. But you have two sets of algebraic numbers or something like that. And one of them seems very real and the other one seems very imaginary, but they're supposed to be like, just
Can you tell?
cousins of each other, mirror images in a sort of Galois way. What were you going to say? Can you
Oh,
tell
I was
what?
asking a dumb question. Can you tell if an algebraic number is real?
I probably don't know the answer to that question.
Yeah,
no matter what the question is.
Actually, I guess.
But I have the feeling that it's going to work out okay. But it did, it took me aback a little bit at first.
I mean, in the absolute Galois group, you can tell what complex conjugation is, right? That's like the distinguished. I'm really getting confused. Do we know the absolute Galois group?
I have a feeling that it's, I have a feeling that, that complex conjugation is an element in the absolute Galois group, and it's very much not a central element. Isn't that right? It's got.
Yeah, you're right. It probably should. Why would it be sent? Yeah, why would it need to be?
So, so I don't know. If I really understood Galois theory, then this would all be very easy. But it's somehow confusing me. What were you going to say?
Okay. So if it's not central, that means there are other subfields of the algebraic numbers that.
Yeah, there are a whole bunch of things that there are a whole bunch of
doppelgangers of the real algebraic numbers.
Yeah. And there's a whole bunch of conjugates of complex conjugation.
Yeah, I know
itself has a whole bunch of conjugates.
Yes.
So I don't know what to make of this, but I just wanted to mention it, and it's something that I sort of.
I mean, the picture. So in your other style of picture.
Yeah.
The Gaussian design that you drew at left does have a very complex conjugation symmetrical look, whereas the one at right,
that's right,
does not. So
that's right. Yeah.
Hopefully that's related.
Hopefully that's related, but I'm not sure I understand things well enough to see how it's related. But yeah. So yeah. So we've got this ridiculous system of equations that has, maybe a couple of hundred solutions or something like that. But we'd really like to understand it better, right? We'd like to maybe, right? So for example, we should be able to add more equations that will rule out the cases where the vertexes lie on top of each other, where the vertexes coincide.
Mm-hmm.
And it's like, right, it's like we have this, the language in which this system of equations is written is a language with limited expressivity. And we're trying to learn how to use this language to say things about the designs that we're looking at. Right, and our big success, as I said so far, is that we actually managed to say something that narrowed down the pool of designs to just a discrete set. So we actually got down to just a zero-dimensional. We managed to.
So you think 700 is still zero-dimensional?
Yeah. Yeah.
I'd say just barely.
But it's not really as bad as 700. It's really more like 200 or something like that. But we're trying to, we're trying to learn the language. We're trying to become more expressive in the language. We want to develop a facility in this language to be able to say the things we want to say. So now, as long as the right, one of the things that limits our expressiveness in the language is if we have to have the coefficients of the systems of equations be rational coefficients.
Uh-huh.
So that's like that's the rational language. So that's right. That's the most restrictive. Well, that's one of the most restrictive languages that we can restrict ourselves to here. So if we only have that limited level, right, we get greater expressivity if we allow like algebraic coefficients in the system of equations. And using that, right, if we have the freedom to use any algebraic coefficients in writing down our equations, then we could, we can speak completely clearly. We can completely disambiguate any one of the 751 solutions from the others. All you have to do is just give the exact algebraic number that completely specifies that solution, and that will do it. But, right, so what am I trying to say? That I was going to say the Grothendieck-Teichmüller orbits, I guess conjecturally, according to big conjectures that people have, the Grothendieck-Teichmüller orbits are the things that you can get down to, the things that you can disambiguate by restricting yourself to using the rational language. Right? I mean, that's the absolute Galois action. So, right, we're trying to understand what the expressiveness is here. So, and right, one of the things we are able to express here is we are able to express the vertex census. That was sort of like, again, the big success here, that just by deciding what the vertex census for the design is, we can express that, the constraint of having that vertex census, we can express that constraint in the rational language. And that gets us down to these 751 or whatever solutions. And, that's progress. But it could very well be that I'm sort of guessing that the rational language should allow us to get it down to just those two particular designs. Because that's what my guess is for the Grothendieck-Teichmüller orbit, that it's just these two designs, these two genus zero designs. And, so we're trying to learn, like I'm saying, I'm trying to learn how to use the language, how to say things in the language. So, I want to rule out all these other designs.
So have you figured out any other thing that's not covered by the?
Well, like I said, like I said, some of the 751 solutions look like they might just be numerical error.
Yeah.
But
I just meant like theoretically, we figured out like stuff you can say about design other than information that's captured by the vertex census that only requires, well, I'm going to say the rational language, even though I'm not quite sure what I mean by that.
Yeah. Was that a full question? Or
that was a question.
Say it again.
That was a question with a parenthetical.
Okay, but can you repeat it again? I sort of got some sense of it, but I didn't get the full question.
Have you figured out anything you can say in the rational language about a design other than information captured by the vertex census?
I think I figured out things we should be able to say, but that doesn't mean I figured out how to say them in the rational language. But I have figured out things that we should be able to say. And this is very much connected.
Only one, because I'm getting sort of frustrated here. Yeah. Can you tell me?
Well, obviously we're running out of time, but this is really going to be connected with the stuff that I've been reading about, trying to learn about what the papers, what the textbooks and papers say about the Grothendieck-Teichmüller group. So I'm going to try to get to say something about that today, but let me try to proceed here a little bit if I can remember what I was going to say. So So what am I trying to say here? Well, I guess, right. I mean, I'm trying to remember what I was emphasizing. Emphasizing that, right. I'm trying to learn, right. I am trying to learn this language. I'm trying to be able to narrow it down much further, from 751 or whatever, down to just perhaps 2 or something like that. And then if I allow myself to use, instead of just the rational language, if I allow myself to use the algebraic language, then I should be able to get it down to just 1.
Yeah.
Right. So, right, running out of time here, but I'll try to say something. So, all right. So I will try to answer your question or address your question. So let me try to state one of the things that you should be able to express in the language. So what you should be able to express in the language is that you should be able to express in the language what is the isomorphism class of the quotient group that we're getting here. So like I say, the big group that's acting on the lozenges here is the free group on 2 generators. But effectively on a particular design, by definition, a particular design only has a finite number of lozenges. So you're just getting a finite group that has 2 particular generators. And if you know the abstract isomorphism class of that group, then you should be able to express that in the rational language. And that's one of the things I'm trying to figure out how to do concretely. But I'm also trying to explain to you and to me why we expect that we should be able to do this, even if I can't do it yet. Well, why I think I should be able to do it. So in other words, right, and that group, that effective quotient group of the free group on 2 generators, that's something you can read off from the combinatorial picture of the design. Right, it's just that. And so why am I claiming that? Why am I claiming that that's a really important thing that we should be able to express in the rational language? I mean, I guess at some point I was even asking myself if that might be precisely the most, not just that we can at least express that much, but I was asking myself if that might even be the most that we can express. I mean, that seems like an excessively precise conjecture to be trying to make at this point. There's probably good reason that that's not quite right true, but it's an interesting question. But okay, but the question that I'm trying to address before we quit here is, I'm trying to address it just a little bit because we're running out of time here. But I'm trying to address the question of why should we hope that we should be able to express in the rational language what is the abstract isomorphism class of the effective quotient group here. And so first of all, let me mention a paper that I've been reading. So this is a paper by somebody named Thomas. I don't know how to pronounce it. I don't know if it's a German name or what. It's like spelled like Willwacher or something like that. And I think it's called something like the Grothendieck-Teichmüller. And it's from maybe like 2014 or something like that. And I think I started reading this paper because, for various ridiculous reasons, it's hard for me to get a hold of all sorts of research materials that are freely available to academic people and stuff like that. But this was one of the ones that I was able to get hold of. And I started looking at it and it looked really interesting. So there's a potentially really interesting paper here that I've been trying to understand. And before we quit, I'm trying to say something about the very first things that I learned about the Grothendieck-Teichmüller group from reading this paper. So what am I trying to say here? So at some point early in the paper, he starts describing a certain short exact sequence of groups, short exact sequence of non-abelian groups. And that it turns out that that short exact sequence is sort of the key to understanding what's going on here. And I didn't understand at first why that short exact sequence was supposed to be so important, but let me see if I can. Let me see if I
need to leave for a minute, and I'm going to pause the recording, and I'm not going to count this off of your time.
Okay.
Yeah. Like
okay.
That'll
give me a chance to think.
Yeah,
Good.
Assuming that's sorry. Let me pause this. Okay. Sorry, I'll be right back. Okay.
All right. So, like I was saying in this paper on the group, sorry, that's supposed to say the Grothendieck-Teichmüller group. I left out the word group there. There's a certain short exact sequence of non-abelian groups that he draws at some point. And let me see if I can copy that from my notebook here.
You need to switch the screen share thing.
Okay, thanks for reminding me.
Yeah,
I'm sure. I think there's actually some, more efficient way where you can show them both on the screen at the same time or something like that. But I'm not quite that competent yet. So I'm looking over here. Okay, so hopefully that's visible now. So now I have to decipher my own handwriting here. So what is it? Okay, I guess he calls this so I'm trying to draw a short exact sequence, which I'm drawing as like what? There's like a monomorphism, and then there's like an epimorphism. And at the bottom, let's see, can I fit that on the page? So he's got a tau fundamental group. There's probably, some better notation for that, but I'll just say EFG for a tau fundamental group of, I think what he's got is the spectrum of the rational numbers.
Cool.
And what he's got at the top is the universal profinite completion. So I'm just abbreviating that as UPFC, universal profinite completion of the free group on two generators. So in the middle, he has a sort of twisted product of these two things. And I think what it is, I think it's a tau fundamental group of the spectrum of the rational numbers adjoined X and also adjoin also adjoin 1 over X. And also adjoin 1 over 1 minus X. I hope I'm doing that right.
Okay, that's nice. So that's
He
some
didn't
kind
write
of
it this way.
punctured sphere thing.
Yeah. And so
punctured rational sphere. rational.
Yeah, and so
line.
this map down here, which is allegedly a surjective homomorphism of profinite groups, is just the obvious induced thing, right? I mean, right? So
Mhm.
maybe I can say, I don't know, not sure how to say that, but yeah, I won't try to write that, but that's what it is. It's the very sensible thing.
Uh-huh.
And you know, then when you take the kernel of this, it just ends up being like that. So he starts talking about this and it gets me very confused. But then I realize at some point what's going on. And what's going on is that, right, I feel really stupid now because this was, it should be obvious. It should have been obvious to me what was going on here. That, right, this is, what are we trying to say? That, right, this is a basic sort of slipping and sliding along a long exact homotopy sequence or something like that. In other words, this looks like a map into this absolute Galois group, right? That's the absolute Galois group down at the bottom.
Mm-hmm.
But right, what this short exact sequence really is that it's the absolute Galois group acting on the homotopy fiber, right? So there's sort of like a, right? I mean, this is how we get the absolute Galois group to act on the designs. I'll have to. This will have to be our starting point for next time.
Uh-huh.
But yeah, the pretend punchline here for now, as we're quitting, is that this short exact sequence has the secret in it. It has the whole secret of how the absolute Galois group acts on the designs. And it's just, you know what I'm saying? It's right, just to anyone who understands how groupoids work in homotopy theory, this should be second nature. So it should have been second nature to me, but in fact, I had to really, really think about it. So,
Okay, well, I don't, yeah, so anyway, I'll just.
well, but
I'll
this is a
quit.
good time to quit, right? We sort of
Yeah,
have to quit now, right?
Yeah, it's okay to quit on a cliffhanger. Yeah, yeah.
It's supposed to, well, it's a cliffhanger, but it's actually also, I mean, there is a sort of punch.
It's not a bad cliffhanger. No one's gonna die. Yeah.
Okay.
Okie doke. Sounds
Okay.
good.
Okay, so thanks a lot. I'll see you.
Yeah, I'll try looking at that paper and then yeah, now I have enough time to actually like do a little bit of stuff so I can.
Maybe I shouldn't have told you the name of the paper, but
Well, come on, it's no fair. You want to try to keep an edge over me? All right. Well, anyway, I need something.
not an edge, not an edge, just. But anyway, yeah, you can go ahead and look at the paper.
Yeah, or something. Yeah. Okay. Okay. See ya.
Okay.